The second drive, using energy from natural sources, is called a water drive, and like the name states, the natural source of energy in this drive is water. In reservoirs with access to aquifers, an aquifer is a layer of earth or rock containing water that can flow and pass through it. The water is used to maintain pressure by replacing all the volume of oil that is produced. This results in a high recovery rate. They can be as high as 70%, but usually average from 35 to 40%. Like solution gas drives, the water drives are used to produce about 1/3 of the world's reservoirs. Now let's look at how a water drive works. There are two possible sources for water drives. One, water coming from a column in an outcrop in a nearby mountain. Or two, any large amount of water under pressure. If you remember from Chapter 2 when we discussed abnormal pressure, we looked at an artesian flow. There we saw that the water was constantly replenished by rainwater at the surface, which then flowed down into the reservoir. The weight of the water column, as it pushed down, generated pressure on the accumulated oil in the trap. Releasing this pressure through drilling pushed the oil out of the trap. In the second example of water drives, a large body of water under pressure stores energy within the H2O molecules like a coiled spring. When pressure is released in the oil reservoir, the water molecules expand and push oil towards the newly drilled well, thus providing the energy for this drive. The rate of water flowing into the reservoir varies greatly in different reservoirs. Again, let's go back to our chart and examine how water drives can be displayed. This time, we'll look at oil production, reservoir pressure with the bubble point pressure, and the producing GOR with water cut. Here, we see the oil production. Notice how it holds fairly steady for a longer period of time than the solution gas line. The shapes of the curves are vastly different and can tell us the type of drive. Oil production holds steady at the beginning because pressure is maintained by the water pressure. Water production can start at any point and will displace some of the oil being produced. This water production will continue to increase as time goes by. We refer to the water production as the water cut. The water cut percentage is equal to the volume of water produced divided by the sum of the volume of oil produced plus the volume of water produced times 100. Notice here that the producing GOR always stays constant because the bubble point pressure is usually never reached. Since water drives have the highest recovery rates, this recovery will be used if water conditions are favorable. The third type of an energy drive using natural energy is the gas cap drive. In a gas cap reservoir, oil and gas were formed at lower pressures, allowing for separation of the oil and gas. These reservoirs are already at bubble point pressure. The energy in this kind of drive comes from the expanding gas as the oil is produced. When a gas cap is present, it is usually better to begin by producing only oil. As the reservoir pressure drops during production, the gas in the gas cap expands and helps to maintain the pressure in the well, forcing oil to the surface. Gas caps that are too large or too small can impede oil recovery. So the effectiveness of a gas cap drive depends on its size relative to the size of the oil zone. Production engineers monitor the gas cap size closely to optimize oil production. When conditions are right and a gas cap drive can be used, recovery rates average about 30 to 40%. The fourth type of drive is gravity drainage. Found in isolated locations where the pressure may have already been depleted or found in reservoirs with very high permeability, the remaining oil will slowly drain into a well due to gravity and can then be pumped out. You can find reservoirs like these being produced in Illinois and Indiana in the United States. The fifth is called a compact drive. Compaction drives are found in abnormal pressure reservoirs. An overpressured reservoir compacts or pushes in on itself, pushing out the oil. Compaction drives are not very common and are found mostly in the North Sea. As you can see, natural energy sources for primary recovery in oil reservoirs use the natural forces found within the reservoir. The volatility of gas in solution gas, the fluid properties of water to flow into an empty space in a water drive, and the fluid properties of gas to expand in a gas cap drive are examples. In addition, gravity and compaction, also common forces, can be utilized to energize drives. To add to the complexity, some reservoirs utilize a combination of these primary drives in the same reservoir and are called combination drives. Now let's look at natural energy drives used in gas reservoirs. There is a drive used in both wet and dry gas reservoirs and another drive in retrograde condensate gas reservoirs. In wet and dry gas reservoirs, the gas within has extremely low viscosity, allowing it to flow readily through the formation to the well. The operation of the gas expansion drive mechanism is therefore quite simple. As the pressure drops, the gas expands into the wellbore. Keep in mind that since gas is highly compressible, unlike oil, its surface volume is much greater than its reservoir volume. For example, 1 cubic foot of gas volume at 5,000 psi in the reservoir would expand to 340 cubic feet at the surface. We know this because we can divide 5,000 reservoir psi by 14.7 atmospheric psi to arrive at 340 cubic feet at the surface. As the well is produced, the reservoir pressure falls to 0. Recovery rates in the gas reservoir run around 95%. In retrograde condensate gas reservoirs, the escaping gas reverts back to liquid at atmospheric conditions. This rich condensate oil is very profitable when the well is first produced because it needs very little refining. However, over time, as pressure drops, the condensate begins to form within the formation instead of in the well. These liquids that build up in the reservoir restrict the flow rate of the gas and cause gas and condensate production to decrease substantially. As you can see in both oil and gas reservoirs, production in its initial stages utilizes the energy naturally found in the reservoir. When this energy is depleted, secondary recovery efforts are initiated. There are several. Water flooding, which uses naturally occurring substances in the reservoir, and thermal flooding, miscible flooding, mobility ratio improvement, and microbial floods, which all use substances that are imported. These recoveries that rely on imported substances are referred to as enhanced oil recovery, or EOR. Let's look at each in more detail. Water flooding is used after primary recovery efforts cease in solution gas drive reservoirs and is the most common. This method recovers about 50% more of what was recovered in primary production. For example, if 1 million barrels was produced during primary recovery, then an additional 500,000 barrels can be recovered using this secondary drive. Water flooding is where water is flooded into the well through injector wells located nearby. Since water and oil do not mix easily, water that is pumped down into the formation displaces the oil, thereby pushing it toward the producing well. This is called fluid displacement. The reason this method is so popular is because water is readily available, cheap, non-flammable, non-toxic, and chemically compatible with reservoir fluids. Its pressure is safe to handle and it works very well. Water flooding works best with lighter oils. Because viscosity is a factor that determines oil's ability to move through the reservoir, its mobility ratio, reservoirs with heavy, viscous oil don't benefit as much from water flooding as reservoirs with high API gravity and low viscosity oil. In this lecture, we've talked about porosity and permeability, and maybe we've given the impression that sandstone, or any reservoir rock for that matter, has constant characteristics throughout a reservoir. This is not true. Like everything else in and on our dynamic Earth, the forces that also help form formations were not always constant or uniform. These fluctuations cause differences in layering of the formation. For example, one layer may have a permeability of 1 millidarcy, another layer may have 500 millidarcy, and another 300 millidarcy, all within the same reservoir rock. Called heterogeneity, these permeable variations cause most reservoirs to water flood unevenly. High permeability zones can take more than their share of the water, which can lead to early breakthrough of water into the producing well. This early breakthrough is called a thief zone. The water literally bypasses the oil, causing it to remain or be left in the reservoir. This unproducible oil is referred to as unswept oil. The water-oil ratio, WOR, of floods can often reach 95% before they become uneconomical. Now please look at this illustration. To help you better understand, let me first explain some of the symbols that are used on these field maps. An empty circle with an arrow through it is the symbol for an injection well. A black circle symbolizes an oil-producing well. An empty circle represents a future well that will be drilled. And an empty circle with 4 lines surrounding it shows a dry hole. Please learn the meaning of these symbols. When water flooding was first used, the injector wells were placed around the periphery of a field. Over the years, however, engineers learned that it is more economical to drill injector wells in the middle of 4 wells instead of just drilling around the peripheral of a field. Illustrating both methods on this illustration allows us to see the differences. The older method on the left forms a peripheral pattern. Its limitation is that sometimes the water doesn't get into the center of the field. To address this problem, the one on the right forms what is called a 5-spot pattern. In this illustration, we see 4 producing wells and 1 injector well in the middle. Keep in mind that an injector well can be an old producing well, or it can be a recently drilled one that acts as an injector well. The water injected from the injector well in the middle pushes the oil to the 4 producers. Because of what is known as pressure drawdown, the pressure in the injector well is different than the pressure in the producing wells. Thus, the oil flows in an X-like pattern toward the 4 producing wells. Unfortunately, this can result in up to 50% of the oil being bypassed or left in the formation. Like I said before, this oil is referred to as unswept oil. To recover this unswept oil, the engineer sometimes drills additional wells that are called infill wells to get this remaining oil. Although expensive, the recovery of this unswept oil, still trapped in the reservoir, may make it worthwhile. Drilling more wells can convert a 5-spot pattern into a 9-spot pattern. It is also referred to as infill drilling.